Hello everyone, welcome back to another video by Endless Engineering. Today we're going to be implementing gradient descent from scratch in Python using a made-up example for linear regression. So in a previous video, I derived the gradient descent algorithm, so I recommend you go back and watch that video because I'm going to be using the same notation here and you might find it hard to follow along. So please go back and watch that video. I'll leave a link in the description below, and there's a link in this notebook here. So from that video, we derived the gradient descent algorithm where we can update our theta parameters using the gradient. And that was done using the minimization of this cost function, assuming that we had a hypothesis which was linear of theta transpose x bar. And there's two ways to implement gradient descent. There's the batch gradient descent and there's the stochastic gradient descent. The main thing being is that for batch gradient descent, we have a number of max iterations that we loop over, and in every iteration we loop over the entire data set and update our parameters. And you know that for a large data set, this then becomes too computationally intensive, especially if you have a large number of iterations. So you can implement the stochastic gradient descent variant where you would shuffle randomly your data, and then you would loop over that data set and update your parameters. So you'd only have to loop over the data set once in the stochastic gradient descent variant. In this video, we're going to implement both of them from scratch in Python. Before we get started, I want to ask you that if you like the way this video is being presented, hit the thumbs up button. And if you have any ideas or suggestions on future videos where we do implementations of algorithms or coding, please leave a comment down below so that I can get some feedback from you for future videos. So we're going to start out with importing the NumPy library and the PyPlot library. NumPy is a great library for allowing us to do a lot of linear algebra and array stuff, and PyPlot allows us to plot the data. I'm going to start out with generating some fake data here with some code that I've written before this video, where I have a line equation and I've set up the slope and the intercept, and I basically corrupt that line with some random noise so that we can get somewhat of a realistic example. And we can visualize that data where x is the input and y is the output, and you can see that you can tell that this is linear and there's noise in the data. Now this is a contrived example, but it's not too academic because there are data sets where you would see such behavior. So I have pre-filled out some functions here that I would like to code with you so that we can get to a solution for the batch gradient descent and the stochastic gradient descent. The first one is where we compute the cost, right? So we know from our equation over here what the cost is, right? We have to sum over the square of the difference and divide by 2 times m, where m is the number of points. So let's start out here by looking at how do I get the number of points passed in. I know, this is the input variable and that's the output variable. So what we can do is we can get the number of samples equal to the length of the input variable or the output variable. It doesn't matter. And then I have to loop over those xy points that are passed in. I really like this zip functionality in Python where you put them together and it just loops through them. And now I can do a prediction, right, y hat, and that's essentially the dot product between the params vector, and here we're not going to do x directly, right? We're going to do what we defined in our previous video on the theory of gradient descent, what we defined as x bar, which is x with a 1 concatenated on top of it. Again, go back and watch that video so you can get an idea of more details. And here what we're going to do after we compute this, we have to compute y hat minus y, and I have to square this, right? That's the definition of my cost. And I have to add this to something, right? So we have to get like a cost sum, and we have to keep incrementing to this. And let's define this before the loop here as 0 before the loop starts, and we can keep summing over this, and we get that sum. After this loop exits and we go through all the data, we can compute the cost as the cost sum divided by the number of samples times 2, right? That's the definition of the cost itself. Okay, so, oops, we have an error here. Oh, forgot to put the in. All right, so now we can compute the cost. Our next function wants us to write some code to compute the parameters using batch gradient descent, right? And so we're just basically going to go through what this pseudocode here says, right? We're going to loop over the number of iterations and then loop over the data set and do a little bit of extra stuff here so we can like retain data. So let me start out with like iteration, right? We're going to start from iteration 0 and we need the number of samples. Oops. That's going to be the length of the input variable, right? We're also going to want to store some values, right? We want to store the cost at every iteration. So let's go ahead and initialize that with some numpy array of zeros or empty or whatever you want of size max iterations. And again here, max iterations is passed in, alpha, which is step size, passed in. The initial value for the parameters are passed in, and both are training input and output data. We're also going to want to store the params. So let's go ahead and initialize that with some zeros as well of max iteration. Okay, so now our first loop is going to be the iteration loop, right? So while the iteration is less than max iteration, we're going to have to do some stuff. And let me beforehand just do this, because I always tend to forget to increment my iterations because I usually have to do it at the end. So I'm going to go ahead and do that now. And we'll start out with, storing the value. So let's store the value of the cost. So cost at this iteration is going to be equal to compute cost. Oops. Compute cost. And what do we pass to this function? We have to pass the input, output, and the parameters. So this we have to pass the entire data set, right? Because the cost is computed. That's how the cost is computed over the entire data set itself and the params. Okay. We're also going to store the current value of the params, right? We want to store everything. We don't want to miss out on what the initial condition actually was. There we go. It's going to be params itself. Okay. And so now we're going to do the second loop of the batch gradient descent, where we loop over the x and y values. Again, same thing as we did in the cost function. We're going to loop over those, and we're going to actually, let me go ahead and copy that from here. This y hat, it's the same computation, right? We're going to compute the predicted value, and then we're going to compute the gradient, and that's going to be this same x bar multiplied by y minus y hat, right? Okay, and after I compute the gradient, I will update my params using that equation for the stochastic, the batch gradient descent. Okay, so let's take a look at this one more time. We come into this function, we have all our input and all our output variables in data set, the params and the alpha and the max iteration. We start our iterations at 0. We allocate some memory to do some storage. We have the first loop, which loops over the number of iterations, and we store our params and our cost at every iteration. And then we loop over our data set and we compute the y hat, which is the prediction, which is params dotted with, this is basically theta transpose x bar. And the gradient is computed with x bar times y minus y hat. And then we update the parameters themselves. What we also want to do potentially in here is to print for every iteration and look at what our cost is, right? So if I print here and I say, this is my iteration, this should be a formatted string, and then I also print my cost for every iteration. That way we can see how the cost is changing over time, and we can see if the algorithm is converging or not. Okay, now that we have the linear batch gradient descent coded, let's try to train our model. So here I'm importing the sklearn model selection module, which has a train test split function. This function allows us to split our data into training and test data by selecting a percentage of how much we want to be test data. And then I'm initializing my parameters. I'm also picking an alpha and a max number of iterations. Let's go ahead and make that 100 iterations. And I'm going to run this function. We get an error. So this error here has to do with how we're storing our parameters, and our parameters here are being stored with only max iteration. We have to make our parameters size like this. Okay, so there we go. This is running, and it ran really fast, and it printed out the data that we wanted to print. Let's go up here, iteration 0, there's the cost. You can see as soon as iteration 1 hit, the cost went down, and the cost keeps actually going down all the way to iteration 99. We get to a point we stop. Now, what you could potentially do is you might have to increase your number of iterations a lot. There might be 1,000, 10,000, whatever it is. So you might also want to implement a early stopping mechanism in your code where you say, oh, if the cost between the last step and this step hasn't changed that much, then stop. But I'm not going to do that in this case, because I want to go ahead and implement also a stochastic gradient descent implementation, so that we can compare both of these solutions and see what they do. So actually for the stochastic gradient descent, it's very similar to the batch gradient descent, where we don't have to implement the iteration loop, but we'd have to implement the loop that loops over the data set. So I'm going to go ahead and copy that from over there, and basically also copy the storage variables where we store everything. We don't need the number of iterations, because again, we're only going to loop over the data set itself. So we have the number of samples, and now our cost size, the array to store the cost, is only going to be the size of the number of samples. And we're going to loop over the data, and we're going to say that computing y hat, which is the predicted value, compute the gradient, and update the parameter. Right? So that's basically it. We need to also store these values for cost. So to get before we had like an iteration number, here what we'd have to do is also introduce some sort of iteration, set that equal to 0, and we'd also have to increment this iteration here inside this loop. Now remember, this iteration is not the same as the iterations in that batch gradient descent, because that's the number of iterations we loop over the batches, which is the entire data set in that case. This is only going to be for us to store some parameters like the cost. So compute cost, give it the input vars, the output, and the params. Okay, and we're also going to store our params. Oh, this is iteration. Right, that's typo. Put that in here. Do that. Okay. So we're storing those. We can also print here, but I'm not going to do that. You get y hat. I'm just checking if this makes sense, and then we get the gradient, and then we multiply, and then we add the params. We increment the param. Okay. So we're going to do the same thing. We're going to have this is a different alpha. This is an alpha here that's going to be used for the batch, for the stochastic gradient descent. I'm going to call this function, which runs the stochastic gradient descent, and we get an error. Oh, that's the misspelled iteration. There we go. And so that ran. It'd be nice if we could like print stuff so we could see it's doing things. Let's just go ahead and do that. I'll copy this from here and put it in here. That way you can see the iterations. So you can see it iterated and went to 79, which is because we have only 80 data sets, 80 data points, right? So again, the stochastic gradient descent might not make a lot of sense for this example because the number of data points is low, but you can see that as we go through the iteration, the cost is going down, and we loop over the data set, which is 79 points, or actually 80 points. Okay, so now we have both models trained. Let's visualize something. So I've written this code, pre-written this code, so we can look at the solutions themselves over the test set, right? So this is a plot that shows us x versus y. So let's add that, right? And what I've done here is I've plotted all the data points which are for training data, and I've plotted the lines that basically correspond to the parameters trained by batch and by stochastic gradient descent. I've also computed some numbers here. These are the parameters computed by the batch gradient descent. So it has a 24, and so an intercept of 24 and a slope of 13, and the stochastic has an intercept of 19 and a slope of 15. And these are the RMS values for the solutions. Now, what the RMS value is, it takes basically the error, and what I'm doing here is I'm taking the error and I'm taking the root mean squared value of it. And this is one metric that you can use to estimate how good your linear model is for regression. The lower this number is, the better the approximation is. So the approximation with batch least squares has 197 and this has 180. So this tells us that the stochastic solution is better. However, what I can do is I can go back and I can add to the number of iterations that I have for the the batch gradient descent. So instead of 100, I can make it 500, and I can run this. And it ran pretty quick, right? And it plotted all those things. And I can look at these numbers again, and you can see that now my batch gradient descent is lower error than the stochastic gradient descent. So in our next plot, what we can look at is the cost. So this is our cost using the batch and stochastic over time, right? That's what we stored. So you can see with the batch gradient descent, we jumped really fast in the beginning, right? And this is because in every iteration, we loop over the entire data set and we update using the gradient. And we converge really fast, right? In this case, we have a relatively small data set, right? So this happens. So if I reduce the step size, you'll see this, become less steep as it converges. It will probably still converge faster here than it would for the stochastic. But if you had a larger data set, then you're better off using stochastic and tuning your alpha. So again, the game here will be eventually, when you have a real data set, large data set, is to tune your step size so you can get good performance of your algorithm and learn the minima or the best fit, basically. And so there you have it. The implementation of the batch gradient descent and the stochastic gradient descent on a somewhat simplistic example, but I just wanted to show you here how you could from scratch implement these two algorithms so that you can train for a linear model. So again, if you like this format of coding in real time, and if you like how we deliver this content, hit the thumbs up button and think about subscribing to Endless Engineering. Maybe leave a comment down below and tell me what you'd like to see differently, or if you have any feedback. Thanks for watching.